Hi everyone. As you know, there are a bunch of CUDA and GPU tutorials online. Most of these tutorials will start the GPU architectures and gradually move into the code. But I think this is not an efficient way to learn the CUDA programming. The best way, from my understanding, is to directly go into the code and check the details and connect the knowledges we have learned before. I suppose you already have some basic knowledge of the C++. So in this series, I will just follow this pipeline. We will read the code and explain the GPU and C++ knowledge together, and then we will run the codes and check the results. This is the first vector add example. We know both CPU and GPU has their own memories, so we first initialize the vectors on CPUs, copy them to the GPUs, do the calculations there, and then copy them back to the CPUs. Let's dive into the GPU code. Here is our kernel. The name of the kernel is vector add, and the global keyword is our gateway. It tells the compiler, this function runs on the GPU, but we call it from the CPU. Notice the arguments. We have integer point A, B, and C. We also use the underscore restrict keyword. This is a crucial optimization hint. It promises the compiler that these pointers do not alias, meaning that they do not point to the same memory location. This allows the NVCC compiler to enable aggressive optimizations, like using the read-only cache, which helps to improve the bandwidth. Inside the kernels, magic happens in parallel. But first, every thread needs to know who am I. We calculate the global thread ID, TID. We can think of the block IDX as the how many blocks per grid. The block dimension is the how many threads per block. And then the thread IDX is individual member. So TID equals to the block index times block dimensions plus the thread index. We also need a boundary check here. If the TID is less than n, then we do the additions. Since we often launch more threads than actual data elements, we need to align with the block sizes. This guard prevents us from access invalid memories and crashing the kernel. Now let's look at the main functions. I'm defining n here, which is the array size, using the constant expression. The constant expression ensures the value is compiled or is fixed at the compiling time, allowing for better optimizations. So the one left shift 16 is a bitwise left shift operation. It is an elegant, geeky way to write 2 to the power of 16, which gives us around 65 key elements. We also calculate the total memory size in bytes using size underscore t. So using size underscore t instead of int is a best practice in C++ to prevent overflow when dealing with large memory chunks. For data management, I'm using the std vector, but here is the pro tips. Always call the reserve before filling the vector. Without reserve, the vector will repeatedly reallocate memory and copy data as it grows, which kills the performance. Reserve allocates the memory upfront. Then we just fill the vectors with some random integers using a simple loop. So my background is the computational fluid dynamics. In a real computational fluid dynamics application, this is where you have loaded your mesh data. After allocating memories on CPUs, we can initialize the data of vector A and B. Note we use the rand brackets to assign the random members. Then we need to allocate memories on the device memories. We need pointers that points to the device memory, conventionally prefixed with D underscore. We use CUDA malloc. Note, M is a big letter here. Unlike C++ new, CUDA malloc requires a pointer to the pointer, so we parse the address of D underscore A. This allocates linear memory on the GPU's global memory, the VRAM. Remember, CUDA malloc is a very expensive operation in high-performance servers. We try to allocate once and reuse. And the second input variable is byte. Next, the data is currently on the CPU. We need to move it to the GPU. We use CUDA mem copy. We parse the destination pointer D underscore A, the source pointer A.data, the size in bytes, and the direction CUDA mem copy host to device. M, H, T, and D are big letters. Note I use A.data to get the raw C pointer from the C++ vector. This transfer goes over the PCI Express bus. It is the slowest part of the pipeline and often the bottlenecks in GPU computing. And then, before launching the kernels, we must decide our execution configurations. I set the number of threads to 1024, which is the maximum block size for most modern GPUs. For num blocks, we use a cell division formula. So here, n plus num threads minus 1 divided by num threads. This ensures that even if n is not a perfect multiple of 1024, we still launch enough blocks to cover every single element. No data is left behind. Here is the moment of truth. We launch the vector add kernel using the triple angle brackets syntax. This core is asynchronous. The CPU continues immediately. However, the next line, CUDA mem copy, with device to host, acts as a synchronization barrier. It waits for the kernel to finish and then copies the results back to the host vector C. And finally, we use the verify results functions to check our results and frame the GPU memory. Use CUDA free. F is a big letter. Please note, never forget to free what you malloc. I want to add one more sentence here. We need to explicitly free GPU memory using CUDA free because CUDA device memory is managed separately from CPU memory and requires manual deallocation. But for CPU vectors, std vector int abc, they do not need explicit freeing. So std vector is a C++ real container that will automatically manage its memory. So that when the vector go out of scope, let's say at the end of the main function, their destructors are automatically called, which deallocates memory they hold. So this is the automatic memory management provided by C++. Alright, we have all parts our vector underscore add.cu code. Notice the .cu extension. This is mandatory. It tells the build system. So this file contains the GPU kernels. To compile it, we do not use the G++ or clan. We use NVCC, the NVIDIA CUDA compiler driver. You can think of NVCC as a project manager. It splits your code into two parts. The host code is sent to your standard C++ compiler, like GCC or MSVC, while the device code is compiled by NVIDIA's proprietary toolchains. Let's build it. So if you see the lower parts of our screen, this is the command line. But we want to speed, so we add the flags. First, -O3. This tells the host compiler to aggressively optimize the CPU loops. Second, and most importantly, -arc equals SM_89. Since I am running the GPU code on our RTX 4000 ADA GPU, the SM_89, sorry, I should put 89 here. 89 targets the ADA architecture specifically. So if let's see if you're on the V100, you can use SM_70. Using the right architecture flag unlocks the specific hardware instructions. Let's compile it. And then you can see our vector add binary file. So what happens when we run this command? NVCC compiles our kernel into PTX, what we call the parallelized thread execution. The PTX is like an assembly language for a virtual GPU. It is stable and compatible across generations. Then, the graphics driver translates this PTX into sets, the actual machine code consisting of zeros and ones that your specific GPU understands. By specifying -arc, we tell the compiler exactly which sets to generate, avoiding runtime compilation overhead. So the compilation is done. We can run it now. Vector add. Boom. We see the output number of blocks 16.4 and number of threads 1024. Completed successfully. So the CPU prepared the data, shipped it to the GPU crunched the numbers in parallel, and sent the results back. Yeah, congratulations. I think we have just orchestrated thousands of threads within a few lines of the code.